Hey guys, today we are going to implement DCGAN from scratch and train it to generate fake human faces for us. This video will be 4 parts, I guess. First, I will give you a Gan Intuition, how guns work, what guns are. Second part will be, I will explain the difference between GAN and DCGAN. You may ask what DCGAN is. The third part will be, we will go over the DCGAN paper briefly and see what's going on. Fourth part, we will do the actual implementation and the training. Before we begin, if you like this video, make sure you smash that like button and subscribe to my channel. What model should I implement next? Let me know in the comment section. And let's get into it. Let's start by having an intuition on how GANs work. The first thing we need to know is that GAN consists of 2 components. The first one is the generator and the second one is the discriminator. The generator is the part that creates the fake things or generate the things that we want to generate. And the discriminator is the part that detects if that thing is fake generated or real. So it is best to understand how this loop or cycle works is with an analogy. In this case, the analogy is that we have an art forger as the guy we can see here, and we have an art inspector, which we can see here. The art forger generates a forged image, and the art inspector tries to detect if that image is real or not, as we can see here. In the beginning, the art forger starts with generating really bad images, mostly only even pixels, okay? But as time passes, it starts to see what makes a real image, because as the forged image goes into the discriminator, it returns a feedback, right? And it starts to see what makes an image real or not. And as the time passes, it starts to create more and more realistic images, so it becomes a better forger. However, this improvement is not one-sided. Also, the inspector, as he has seen more fake and real images and compared them, he starts to get a better idea on what makes an image real and what makes an image fake. So our inspector becomes a better art inspector, and our art forger becomes a better art forger. This creates this loop where they make each other do their job better. And this is what gives us hyper-realistic images. And this is the power of GAN. The second point I want to discuss is that you may ask what is the difference between a regular or vanilla GAN and a DCGAN. And the answer is actually fairly simple. A GAN with a CNN is DCGAN. That is a broad picture, of course, but the main difference is that instead of using any fully connected layer or anything, we will use CNNs in their place. Before moving on to the coding part, it's time for a quick paper overview. So this is the paper where DCGAN is introduced. And DCGAN, the name comes from here. Deep Convolutional Generative Adversarial Networks, for short, DCGAN. Let's look at the abstract. So it basically says that the CNNs have tried for GANs, but it has failed. But now they are introducing new class of CNNs, which is DCGANs, DCGANs. And we have the introduction, the related work, but the main thing, two main things actually. The first part is here. It gives us information about the implementation. For example, they replace any pooling layer with strided convolutions for the discriminator and fractional strided convolutions for the generator. They use batch norm in both generator and discriminator. They removed fully connected hidden layers because we will replace them with CNNs. They used Rayleigh activation in generator for all layers except output. In output we will use tonnage. You will see this. And the use of leaky Rayleigh activation in the discriminator for all layers. You will see this too. So it gives information about the training. By the way, we will come back to the paper during the implementation to get the hyperparameters. But the other thing that we should look at is here. As you can see here, this is GZ, which stands for the generator. This is the architecture of generator. We get 100, which is the input vector dimension, which will be noise. In this case, we will be feeding noise to the generator. And that noise soon will become realistic images. And as we feed different noise, we will have unlimited number of output images. So we will adapt this approach for the generator, and we will use its reverse for the discriminator. And what discriminator will do is basically it will be a binary classifier to classify an image on whether it is fake or real. So let's get to the coding. The dataset that we are going to use is the celeb faces attributes, which is celeb A dataset. I will give this link below. You will just come here and download everything, okay? You just click this and download every file, put them in a directory, and then switch to your notebook. As a notebook, you can use any notebook you like. In this case, I'm using Kaggle's notebook. Why? Because it is easier to load the data, I don't have to download it, and it gives me some free GPUs. That's the reason. So let's get into the implementation. Let's zoom it a little bit. Now, okay. First, I'm importing some libraries, starting with importing Torch, which is our main library that we will use. Then I imported NN from Torch and Optim because we will define optimizer from this library. We imported the data loader, that is for the training part. We imported transforms because we will do some data augmentation during the training. Image folders, again, instead of a dataset, if you have images in a certain folder, you can just load them into a dataset with this image folder function. VUT is from Torch Vision. It is for some visualization. Matplotlib, PyPlot, this is for plotting our results. Random, we need random, NumPy, time it, and NumPy to set the random seeds. Time it, I like to estimate the training time, that's why we need it. And finally, TQDM, we will print a pretty progress bar with TQDM. Okay, now it's time to define hyperparameters and some other things. Let's run this first. Okay, first we have to give data directory, okay? This is the directory where your images are located. So it's supposed to be just under celeb dataset image lane celeb A. If you give this path, it's just fine, okay? The next thing is the batch size. It depends on your GPU. I could fit 1024 batch size to my GPU, so I gave that. Image size is 64. So this is the image size for this dataset. Same with channels. Images has 3 channels at this dataset, RGB. Input vector dimension. So let's switch to paper. It is this guy over here. Okay, this is what we feed to the generator. Its dimension, and it is 100. So we will use 100 in here too. Feature map dimension. So we will use it during the definition of generator and discriminator. This is how we define the shapes. Learning rate. Let's go to the paper again, and learning rate, let's type it. So it says suggested learning rate is too high, so they are using 0.0002 instead. So we will directly copy that from the paper, and learning rate is 2e-4, which is the same as this. Additionally, we are going to use ADAM as an optimizer, and the paper gives us a beta 1 value for that. And here it is. It says that default value suggested is 0.9, results in oscillation and instability. So they switched the beta 1 to 0.5. So we will directly copy that too. So beta 1 is 0.5. Epochs, so 2 is too short, okay, it is too low. Since this is a demonstration, I set it to 2, but the higher the epoch number is, in this case, the better it is going to be. Since it is just a demonstration of how it works, I set it to 2, but if you want to see the real quality images, set it to higher number. A random seed, I gave it 42. This is just to keep things reproducible. So this is for hyperparameters. So let's switch to here. What I did here is basically I set the random seeds. Okay, so for the random, I set the random seed. For the NumPy, I set the random seed. For Torch, CUDA, and backend CUDANN, I set the random seeds. So this makes sure that our results are reproducible. Next thing, we have to give a device. CUDA if you have GPU, and CPU if you don't have it. That's what it does. Now it's time to implement our first part of the GAN, which is the discriminator. So what discriminator does is, as we mentioned, it will just classify the given image as a fake or real. And how we are going to implement it is just reverse of the generator, okay? We will take the generator output, we will take the same architecture here, and we will reverse it. So I will give it in images as a reference. I will put it somewhere here. Let's zoom out a bit. Okay. Another thing to note before moving to the discriminator is, let's go to the paper again and look at here. For discriminator, we will use straighted convolutions, which is just conv-d in PyTorch. We will use batch norm in both generator and discriminator. Remove fully connected layers. We did that. We will replace them with strided convolution or fractional strided convolutions in case of generator. Use leaky ReLU activation in the discriminator for all layers. Okay. So let's start the implementation. First, if you look at the generator, we will take its reverse. We can see that there are 5 layers in total, 5 convolution layers. So what we do is we will take the image, which will be the input over here, and apply that operations to classify that image. First, let's define the convolution layers. So the first convolution layer will take the input image and map it to a convolution with size 228 to 32 and 32. As you can see, that is the first part, the first dimension of our operation. So by the way, while implementing it, I find that the most important thing is the keeping track of the sizes of your tensors. The second convolution operation will be taking that first convolution, taking its output and map it into to size 256 to 16 to 16 to 16. The third one will be taking the second one and mapping it to 512 to 8 to 8. And the same process for the fourth layer, taking the previous one, mapping it to 1024 to 4 to 4. And the last operation is the result of classification, which is 1 or 0, real or fake. So this will output just once. As stated in the paper, we are going to use leaky ReLU for discriminator and batch normalization. So batch normalization dimensions are in alignment with the convolution. As you can see, this is multiplied by 4, 8 and 16, same as this, 4, 8 and 16. This makes sure that there are no mismatches in the dimension. And as a result, we will do a sigmoid to classify it as a 0 or 1, fake or real. Now let's apply the actual operations with this forward layer over here. By the way, I forgot to mention that as arguments, we will take feature map dimensions and channels to our init. Alright. Let's go to the forward. For the forward part first, we are applying the first convolution to our input. Then, as stated in the paper, I'll show it again. Here, leaky ReLU and batch normalization. We apply leaky ReLU to it. Then we take it and feed it to the second convolution. We apply a batch normalization and leaky ReLU. Feed it to the third convolution. Apply a batch normalization and another leaky ReLU. Fourth convolution, another batch normalization, another leaky ReLU. Fifth convolution and sigmoid as an output, and we return the output, okay, which is this. So here we define our discriminator. We give feature map dimension and channels as arguments. So as we stated, feature map dimension is 100 and the channels, since we have RGB images, channels is 3. And then let's just create a dummy image and test if this works or not. By the way, let's run this. Let's test if our discriminator works or not. So I created a dummy image here with random integer. It is basically a noise, okay? I gave it batch size, channels, image size to image size. This is a dummy image. I defined the discriminator here and I fed the dummy image to discriminator here. And if everything goes well, I expect to be the output of this size, which is the classification output. So let's run this with batch size, of course. As you can see, 111 with batch size of 2024, which we defined in the beginning. So discriminator is working as expected. Now let's move to the generator part. For the generator part, we will use exactly the same architecture again given in the paper, and a couple of other things to note before we begin. We are going to use fractional strided convolutions in generator. So what they are is they are conv transpose 2D in PyTorch. So we will use these convolutions. Again, we will use batch norm in generator and discriminator. Here are our batch norms. And we will use ReLU activation in generator for all layers except the output, which uses tan_h. So here our ReLU function and here our tan_h. So according to that, let's put the image here and start implementing. Find the generator that takes it from NN module. As inputs, we took input vector dimension, feature map dimension, and channels. And as usual, super generate itself, since this is a PyTorch class, okay. And let's start to define our convolution transpose to these. As you can see in the image, after we get the input, we mapped to a convolution with size 2024 to 424. So we do that with this convolution transpose to D. We take the input vector dimension, we take the future map dimension, multiply it by 16, and these are to make sure that results are stable and dimensions stay the same as we want. For the second convolution, we do the same thing. We take the feature map multiplied by 16 and we multiply the output channel with 8. So this gives us size 512 to 8 to 8. For the third convolution, we take the feature map dimension multiplied by 8, and we multiply the out dimension with 4. So this gives us a size of 256 to 16 to 16. The fourth one will give us the same procedure. It will give us size of 128 to 32 to 32. And the last convolution operation, which we take future map dimension multiplied by 2 and output with channels of 3, will give us an output of 3 to 64, 4 to 64, which we can see in the images. So what this is it is an actually image. So this is an image with 3 channels and 64 and 64 height and width. So this will be our generated image in the end. After that, we generate our value as we just saw, just like stated in the paper. After that, we define our batch normalization 2D, again with feature map multiplied by 16, 8, 4, and 2. And as stated in the paper, we will take the tan H for the last layer. So let's go to the forward implementation. We take the input, we first apply the first convolution here, we take output of that, we apply normalization and we apply ReLU. Same thing for the second convolution, batch normalization and ReLU. We are feeding output of one as an input of the next. We do it for the third convolution, batch normalization, ReLU. Fourth convolution, batch normalization and ReLU. However, in the end, we won't use any ReLU, just we discussed. We apply the fifth convolution and we use tan H to take the output, which gives us the output, which is the generated image. So let's run this. As usual, before moving any further, let's verify that our model works. So we define the generator here, input vector dimension, feature map dimension, and channels as inputs, like we have here. After that, we will create dummy vector, which will act as this 100 here. So it is batch size, input vector dimension, which is 100, and 1, 1, since this is just a vector. And after that, we feed that noise into our generator and see our generator out size. So what we expect is batch size 364 to 64 as the output size. So our batch size is 1024. We expect a size of 1024 to 3 to 64 to 64. Let's run it. As we can see, output size is 1024, which is the batch size, to 3 to 64 to 64, which is an image. And this overlays with what is stated in the paper. So we can go with doing the actual training. For preparing the data, we can use just a very simple formula. Since our data consists of only images, we will use this image folder function, which we imported during the beginning. What it does is it just takes the directory for your images and creates a dataset for you automatically. So here we define dataset and we give the data directory as an argument. After that, we want to have some data augmentation and preparation. So what we do is we will apply transforms. First, we resize according to the image size. We will crop according to the center and with image size. Then we will convert it to center. Finally, we will apply a normalization. So this basically returns us a data set. Pretty simple and straightforward since it consists only images. After that, we define our data loader. We define it like this. We take the data loader, we give the data set, we give the batch size, and if you want to shuffle it, in this case we do, we say shuffle equals to true. And our data loader is ready, and we can train it with iterating it. Let's run this. By the way, it may take a while for this to complete, okay, for this to create the data set, so be patient. By the way, while it is running, let's talk about the actual training loop. First, let's define the loss function, which is criterion. We will use BCE loss here. Since we have two models, generator and discriminator, we will have two optimizers as well. And as stated in the paper, which is here, ADAM, we will use ADAM optimizer, okay? So what we do is optim.adam. We will first give the parameters of whatever the model we are using. In this case, discriminator.parameters. We will define our learning rates and we will define our betas like this. we define the beta one as 0.5 according to the paper in the beginning of the video. We do the same for generator, as only difference is as the parameters part we will give it generator.parameters. Let's zoom in a bit to the code, by the way. Next thing is we will put the generator and the discriminator to the train mode. We will start a timer to estimate how long the training is going to take. So let's start the training loop. For each epoch, we will iterate through the range of epochs. We will do it inside TQDM so we can see the progress. And if we are on a notebook, if you say position equals to 0 and leave equals to true, it will prevent the TQDM to write the same line again and again, and it will actually update it in a single bar. So we will need to keep track of the generator and discriminator losses. So we will make them to zeros in the beginning, and we will start to iterate the data loader. Again, for index and data, and we will do an enumerate. So index will actually keep track of which iteration we are in, and the data will be actually an element of the data loader. So TQDM data loader, so we are iterating the data loader basically. Again, we use TQDM to keep track of the iterations and position 0 and leave equals to true, so that it will update the same progress bar over and over again. By the way, I find that the most complicating part about GANs is the training, because we are training two models at the same time. Keep an eye here. The first thing is we will take the image data. We will take the image data zeroth of this and we will put it to device. Why zeroth of this? Because the first one consists of labels. So image data size will be 1024, which is the batch size, to 3 to 64 to 64. And this is image, as you can see, with 3 channels and 64 to 64 dimensions. And we have dummy labels, which consists of the first index of the data with size of the batch size, in this case 1024. After that, as we discussed, we will need two types of data. First, real labels. Second, fake labels. So real labels, what it does is that it just consists of ones. It will just consist of one in this case, to denote that image is real. And fake labels will consist of zeros that will denote that the images are fake. So what we do is we say torch.fill to fill the tensor with our value which we like it to fill. We take dummy label.size, which is a vector of 2024, which we can see here. We want to fill it with ones, which stands for real labels, and as a data type we want it to be float, and we'll put it to device. We do the same thing for fake labels, but only difference is that instead of filling it with ones, we will fill it with zeros, which will stand for the fake labels. We will use this real labels and fake labels to update the loss. And finally, we will need a noise. Why? Because we will feed this noise to our generator, so that it can create an image for us. This noise will be input of the generator, so it will be a size of 100 to 1 to 1, just like we showed when we were coding the generator, and just like here. As you can see, 100 to 1, a vector. So what we are going to do is, again, we will say torch.random integer, and we will say dummy labels.size. We will take the size of the dummy labels and we will take the 0th dimension of it, which this is the becomes the batch size actually, by the way. And as a second dimension, we will take the input vector dimension, which is 100, and the next two will be 1 since it is a vector, and we'll put it to the device. Now we are going to take our first output starting from the discriminator. The first one part is we take the real image, which is the image data, we feed it to the discriminator, and we get the output for the real image, classification output. And we will do a view -1 because as a result, if you remember, when we implemented the discriminator, it will give us the result and 2 more other dimensions. So we don't want that dimensions, so we just do view -1. And it just makes it a size of 1024. So that's why we put the -1. So this will give us a tensor of size 1024, which will consist of discriminator's prediction for every image in this batch as a real or fake. So this 1024, every one of them is actually equals to an image, and every one of them, this discriminator's output will have a classification result as a 0 or 1, and we assign it to discriminator real out. After that, since we fed the real image data, we have to get it lost. So how we do that is we take the criterion, we put discriminator real out, which is the output, classification output of our discriminator, and since we are trying to classify the real labels now, as a second argument we give the real labels, because we fed the real labels, so that is the ground truth, and we give real labels to calculate the loss hence. After that we do zero grad and discriminator real loss dot backwards to make sure learning is happening. Now we fed the discriminator the real image. Now the discriminator knows how a real image looks like. The second step is to teach the discriminator how does a fake or generated image looks like. So where do we get the generated image? From the generator. So we will take the noise that we defined here and we will feed it into the generator. It will give us an image output, which is with size 1024, which is the batch size, and 364 to 64, which stands for an image. We will put that into the generator fake out. This is our fake. This will be a batch of fake images or generated images by the generator. Now we take the discriminator again and we give the generator fake out as an input. So we ask the discriminator to classify these fake images, generator images. An additional thing I added here is detach. If you realize what this detach do is that since we are training two models at the same time, we will use this discriminator fake out again while training the generator. But if you don't do this detach, it will give you an error saying that the computation graph is not deleted, something like that, because we are writing two computational graphs on top of each other. So if you do this detach, that error will disappear because we detached it from this current computational graph. So that's what we want to do. View-1 the same. It will give us the result of a batch, which is 2024, and it will give us an additional 2 dimensions which we don't need. So we will say view-1. So we end up with discriminator fakeout, which is a discriminator results for classifying the generated images, which is the output of the generator. Again, its size is 1024, just like the discriminator real out. So while calculating its loss, again, we will put criterion. However, since we ask discriminator to classify fake images, we will compare the output of the discriminator, which is the discriminator fakeout, with fake labels. Just reverse of what we did. After that, we do backwards to make sure that learning is happening. We calculate the loss for the discriminator. We first take the discriminator with real images and fake images and we sum them up and we say optimizer that step. So at the second step, we gave the fake generated images to the discriminator and made the discriminator learn what does a fake image looks like. I hope it is clear until now. I will do a quick recap. So we trained discriminator 2 times until now. The first one is we fed the real data and teach discriminator how does a real image look like. At the second step, we fed the discriminator the output of the generator, which is a fake image. We teach discriminator how does a fake image look like. Now, what we are going to do is actually teach the generator how to produce better images. So here we come to this line and actually run the discriminator again with the generator outputs. Why we do that is we will update the generator by the output of the discriminator. Remember, in the beginning we mentioned that it is a loop and they make each other to do a better job. So we will take the output of the discriminator with generator outputs and create a loss with that, with the output of the generator with fake images and real labels. So why we do that is that we want the generator to be close to real images as much as possible. Yeah, right? That is the whole purpose. We want realistic images. So we take the discriminator's fake results outputs, which is the output of the generator, and we take the criterion with the real labels so that the generator can learn when did the discriminator classify its outputs as fake, and by that it will learn where to improve to make more realistic images. So that's what this line does. After that, we update the generator running loss and we zero grad the generator loss start backward and step. Do this to make sure that learning is happening for the generator. After that, we just update the losses. Discriminator loss equals the discriminator learning loss divided by index plus 1 multiplied by 2. Why did we multiply it by 2? Because we trained discriminator 2 times in one loop. That's why I multiplied it with 2. For the generator loss, it's just generator running loss divided by index plus 1. Okay, I hope it is clear till now. I will quickly recap the training loop. Like I said, the critical part of GANs is understanding the training loop. So first we take our real image and we take some dummy labels from their data. We filled that dummy labels with placeholder for real labels, which we called 1. And we filled it with placeholder for fake labels, which is 0. And we created a noise to feed into the generator and generate an image. After that, we take the discriminator, fed the real data, and calculated the loss according to the real labels, so that discriminator will learn how does a real image look like. At the second part, we take the output of the generator with noise, the fake image. We ask the discriminator to classify that fake image, and we calculated the loss function according to the fake labels, so that the discriminator will learn how does a fake image look like. And we made sure that learning is happening. At the last part, we calculated the discriminator with fake images again, and we calculated the loss function according to this fake outputs of the discriminator and the actual real labels, so that generator will learn how does the discriminator classify the fake images as real, so that it can improve in that area. After that, we updated the losses and made sure that learning is happening. We print out the losses for each epoch at these 2 lines, and for each epoch I added this so that it will print 3 to 3 grid and show us how does generator improve and how it is doing. So I will explain this too. We just created a figure and we created a subplot for that. We set the axis off and we gave it a title, the name of the epoch 0, 1, whatever, generated images, and we use VUTs from Torch Vision, made a grid. We took the first 9 generated images from the generator, which is generator fake out, which we can see here, the output of the generator. We gave some padding normalization and we want it to have 3 rows, and we put it the CPU. And if you want to plot an image, so currently it is like this, 364 to 64, which is input number of channels to dimensions. We have to map them as 1 to 0 so that we can show the images. This thing does that, and we just show the generated images, 9 generated images for each epoch. At last, we just stop our timer and print the elapsed time. So let's run the training. Like I mentioned, since this is only a demonstration, I made it 2 epochs, but if you want realistic images, set it to a high number. After the training completes, let's meet here again. Now our 2 epochs of training is complete. Let's look at the results. First epoch, you can see just blurry faces. At the second epoch, we actually started to see that the faces are forming. If you keep this going, you will end up with more and more realistic faces. So for now, let's keep it at 2 epoch for demonstration purposes and continue. The next thing we want to do usually is to empty the cache of CUDA so that we won't run out of memory. So let's run this and let's actually print some more images between real and fake and see what's going on. For that, I just defined an iterator called realBatch. As the previous one, I started a plot, we create the subplot, axis is off, and title I gave it real images, and I showed the image with PLT. I used VUTs from Torch Vision and we made grids. We took the 0th batch from it. The first batch, it already contains 1024 images, so you won't run out, no worries. We only took the 9 of them. We do some padding and we want 3 rows, so it will be a grid of 3 to 3. We put it the CPU, and this, if you want to show a torch image, you have to change the dimensions. So we will just do 1 to 0. That's for that. And we will do a very similar thing to show generated images. Instead of saying real batch 0, we will just use the generator fake out. This will come from the last epoch. So these will be the latest images, and we will take 9 of them, 3 rows, and we change the rows of the image. And let's show it. As you can see, these are the real images and these are the generated images. If you train for more epochs, it will become more realistic. What to do if you want to generate a single image? That is simple, just like we did in the training. We create a noise. I actually copied and pasted it from the training part directly, to be honest. You just create a random number with dummy label size 0. You take the 0th dimension, you put the input vector dimension, and you put it to device. You already have the trained generator. You put the noise here and generator fake, and the generator will actually give you an image. We will just say plot.imshow, and since this is a batch of 1024, you can choose any image out of the 1024. I wanted to showcase the second one. I just detached and put it to CPU so that it won't take space. Again, we put it to 1 to 0 so that we can show the tensor image, and let's hit enter. And this is a generated image. We can look at other ones, 5 or whatever. So as you can see, the quality is currently very low. Since it is a demonstration, I trained it for only 2 epochs. If you want more, go for more epochs. And this was the DCGAN done.